All right, so there's only a couple other techniques I want to show you from this section, Chapter 5, Section 1, and we'll get to those in just a second. I want to point something out, something that you might find fairly interesting. So you probably remember your compound interest formula, and I'll tell you really quickly what each of these little variables represent. So we'll actually start with the right side. So the R is just the rate of interest written as a decimal. We want to make sure we write the interest as a decimal. So that's the rate of interest. The T represents time, and it's actually time in years. The P represents principal, and again, I'll make sense of this in just a second. The N represents the number of times your interest is compounded, right? So if you might have a credit card that's compounded monthly. So in that case, N would be 12. Now, A represents the amount, and here's what you should do when you have time. And if let's assume that you are looking at two different. I'm not going to go through this in detail, but this is something you really should do if you want to try to figure out how much college is really going to cost you. What you should do is, let's say you were debating between two different universities. Let's say one of them was private, one was public. Now, you should think about how much money you're going to have to borrow, let's say over your 4 years. That's if you can complete your 4-year degree in 4 years, which is an anomaly anymore. But let's say you can figure out how much money you have to borrow to complete your college. That would be P. And then what you would do in a case like this, you can make this easy. You can just let N equal 12. The interest rate for student loans is normally capped. I don't know that for sure. So again, it's been a long time since I've been in college. You might look this up online, but it's probably about 7%, something like that. Another thing that you should look up, let's just assume that you're average. A lot of times we inflate our egos. But if you are average, it's going to take you 25 years to pay off your student loan. And you should assume that you are going to be average, the average individual, for how long it takes to pay off your student loan. You really shouldn't think of best case scenarios. So in this case, again, you should fact check, but it's somewhere around 20 or 25 years. So if you had to, let's say, borrow, $10,000 a year for 4 years, let's say plus books and everything else. Let's say for one institution, you would let this P equal 50,000 maybe. And then if you were thinking a private school, or maybe it was 30, 40,000 a year, everything else, this P might be 150,000 or 100,000 a year. And you should run the exact same numbers. Okay, T would be the same, 20, 25 years to pay off your student loan. R would be the same, say 7% interest for both. N would be the same, let it be 12 if you want. And the only difference in the two calculations would be how much you cost to borrow to go to a public institution, how much it costs to go to a private institution, and you can, on your own time, figure out how much college is really going to cost you. And then you should consider the payoff, because I would never try to talk anyone out of going to college. But if this is $1.5 million, which very well can be if you're picking a private school, if it costs you over $1 million, say, to finish your 4-year degree, it is going to take you a long time to pay that off, and you're going to have a huge monthly payment along the way. And I just hate to see bright young students come out of college with basically a mortgage or more just hanging around their neck, and just weighing them down for the rest of their life. But that is not why I chose to write this. I tell you what, just in case you'd already ran those numbers, and you're depressed right now. Hold up for just a second. You can also start to think about how much money you might have instead of that P being how much you're going to borrow. Let that P be how much money you're going to invest. Okay, over 20 years, 25 years, and then you can start to be happy, start smiling, right? This guy right here. Ready? So I want to show you something that I think you're going to find fairly interesting. So let's create a fictional example, right? Just a fictional example for this compound interest formula. Let's make things really simple. Let's let principal be $1. So P equals 1. Let's let T equal 1 year. And let's let R be 100% interest. Like a loan shark, right? Or in other words, just R is equal to 1. So I'm letting P equal 1, T equal 1, R equal 1. How would I rewrite my compound interest formula? Well, this would be 1 times 1 plus 1 over n. And then n times 1 would just be to the power of n. Now here's something fairly interesting. Ready? What I'm going to do is we're going to just pick some values for n. And then we're going to plug them into our 1 plus 1 over n to the power of n. Let's do it. Right? We're not going anywhere. We're in quarantine. So let's start with n equals 1. I'm just going to do these calculations for you. Ready? First, I'm going to clean that up to the power of n. So let's let n equal 1. Well, 1 plus 1 over 1 to the power of 1 is 2. All right, well, let's let n equal 10. You would get about 2.59374, something like that. What if you let n equal 100? Well, you get 2.70481. Ooh, hold on. What if you let n equal... I'm not even going to play this game anymore. I don't have my calculator in front of me. What is this number starting to look like? 2.70481. I think we've seen something like that. 2.71828. Interesting. So here's what's interesting. If you keep choosing larger values of n, in other words, as n approaches infinity, what does 1 plus 1 over n to the power of n approach? It converges or approaches e. Interesting, right? Interesting. Okay, so two more techniques. It's more of the same. It's just I want you to be ready for a couple other things. Ready? So let's take a look at this guy. 2 more problems. Now, this, you want to differentiate, right? You want to take the derivative of this. And I'm telling you, if you give me 2 calculus students beside each other and one's working, they're just working insanely hard on a problem, and the other one just seems like they're breezing through it, I will guarantee you that the first is trying to take the derivative the way it sits, and the second just noticed that, hey, I can rewrite this. It doesn't have to be this complicated. And that's what we're going to do. We're going to rewrite this using those log properties, right? The log properties, I've reproduced them down at the bottom here. So let's start. The very first thing I'm going to do is, I have no log properties yet. The first thing I'm going to do is rewrite this radical using a fraction as an exponent, right? Let me do that first. So if I rewrite f of x, I just want to get rid of that radical right now. So that's going to be ln of, I'm going to use some big brackets so you know, that's x times x squared plus 1 squared over, no more radical, let's use 2x, that is to the power of 3, I believe, minus 1 to the power of 1/2. Okay, ready? And now, let's start to notice some log properties here. So I'm noticing a quotient. So we should be thinking the quotient rule down here. I'm also noticing a product. So we should be thinking a product rule. You are going to always start with that quotient. So let's do that really quickly. So the very first thing I'm going to do, right, I'm going to use that use that ln of A minus ln of B. I'm going to do that right now. Let me give myself a little bit of space here. Okay, so that's going to be ln of the numerator, which is x times x squared plus 1 squared, minus what? Minus ln of the denominator. And so that's minus ln of 2x cubed minus 1 to the power of 1/2. Now I'm going to delete those log properties in just a second, but just to give me more space. But right now I'm stuck in the rewrite phase. So the next thing I'm going to notice is that I have a product here, right? And I want to use my product. I'm going to use that ln of A, right? ln of A plus ln of B. I'm going to use that product rule. So let's do that now. So that gives me ln of, now we're going to, A is going to be x, so that's going to be ln of x plus ln of, I got x squared plus 1 squared. All right, and I still have my minus ln of 2x cubed minus 1 to the power of 1/2. All right, and that last rule that we're going to use is we're going to use the fact that you can, rule 3, where you can bring the exponent, this exponent here, I can bring it out front. This exponent here, I can bring it out front. Okay, so as of now, I'm going to go ahead and get rid of these log rules. And let's go ahead and rewrite this. So now I have ln of x plus 2 ln of x squared plus 1 minus, let's bring the half out, so half of ln of 2x cubed minus 1. And what I'm telling you is what started off as this really complicated derivative, because of those log properties, we were able to break this up. And now this is going to be so easy to take the derivative of. Ready? Let's finish it. So finally, no derivative has been taken yet. So it's at this stage right here where we say f prime of x equals. Ready? Let's go down the line. So the derivative, let's start here. The derivative of ln of x is just 1 over x, right? 1 over x. Okay. Now the derivative of 2 ln of x squared plus 1, don't you remember that u prime over u? So that's going to be plus 2, and it's going to be u prime over u right here. Plus, it's actually minus 1/2. And again, we're going to have u prime over u here. All right, so in this case, you would let u equal the x squared plus 1, and then u prime would just be 2x, and then over here, you would let u equal 2x cubed minus 1, and then u prime would end up being 6x squared. So let me go ahead and write that. So that ends up being 1 over x plus 2 times, well, u prime is 2x, and u is x squared plus 1 minus a half. All right. Well, if you let u equal 2x cubed minus 1, then u prime would just be 6x squared. Okay, now I'm going to leave it here. You would clean that up. You would bring this 2 up here. 2 times 2 would be, that would be 4x. And then you can distribute that half. So you could just take half of 6, which would be 3. And then you would be done. You would actually have the derivative, and all you had to do was just use those log properties to make your derivative a heck of a lot easier. All right, now notice in this example, and this is a very, very good example of how you can start to use your log rules. You really should have this in your pocket. What I'm going to do in this case, this is not, well, let me go ahead and do it this way. Let's go ahead and rewrite using, or let me say it this way. Let's just stop. Do you see an ln anywhere in this problem? No, right? And do you agree with me that this looks like a complicated, or at least cumbersome derivative to have to go through? There's a lot of chain and quotients going on there. So I'm telling you that you can take ln of both sides of this equation right from the beginning. If I take ln of the right side and ln of the left side of the equation, I can now use those log properties that we used in that previous problem. Okay, so let me now just go ahead and rewrite this using the log property. So that's ln of y is equal to, now will you allow me to just to go ahead and simplify this, right? I mean, you got a quotient rule, ln of a minus ln of b. You got to bring the 2 out front. You got to turn that into a fractional exponent. So please just allow me to rewrite this. So this would be 2 ln of x minus 2 minus 1/2 ln of x squared plus 1. Okay, now if you don't mind, let's just assume that you, well, either pause the video and see if you can make it through that, or just accept that if you took a time that you could go through those log properties, okay? So last problem of this section. What we're going to do now is, remember, we want the derivative. So if I take the derivative of both sides right now with respect to x, now I'm going to write, this is d of dx here, but I also have to take the derivative of the left side, d of dx here. Now, listen to me. That might look weird because you're thinking, oh, well, normally I just take the derivative of the right side, but no, you don't, right? If you think about, if you have y equals 2x, you do take the derivative of the left side when you write dy dx, and then you take the derivative of the right side, which is when you write the 2. It just so happens that when it's solved for y, we really think about the derivative process being over here, right? And then we just have dy dx on the left side. But you do take the derivative of both sides of your equations, even if it's explicitly defined. So let's go ahead and do this. The derivative of ln of y, well, the derivative of ln of x is just what? It's just 1, or it's 1 over x is normally the way you write it, but since we have y, we're going to think of it as u prime over u, right? I should have wrote that as, I'll write that as y. So in this case, we're going to get, if you let u equal the y, then u prime would just be y prime. Okay, with me so far? All right, now let's go through and take the derivative of the right side. So this would end up being, we got 2, all right, and then this would be u prime over u. So if you let u equal your x minus 2, then what would u prime be? Well, u prime would just be 1 minus 1/2, and then you would have u be equal to x squared plus 1, and then of course u prime would just be 2x. Okay, now this is not a derivative, right? You have to solve for y prime. So we can solve for y prime by just simply multiplying both sides of the equation by y. All right, I can bring the y over here. Now, the only thing I'm going to do right now, and this is, for some, this is going to be annoying to many of you. I'm going to go ahead and simplify this. I'm going to, because I don't want to have a y here and a y here when I bring this y over. So here's what's going to happen right now. Here's what's going to happen. I'm going to distribute those 2's, 2 here, 1/2 here, and then I'm going to have to have 2 different fractions that I'm going to combine into one fraction. Okay, and I'm going to do it without showing you any of the work. Why? Maybe because I'm lazy, or maybe just because you should know how to do that. So this is not mathemagic. It's just me simplifying that right-hand side of that equation. Okay. And now I'm going to, I had 2 fractions, I got them into one fraction, and now I'm going to take this y, bring it over here, so that I can solve for my derivative. If you're like, what's going on right now? Don't you want the derivative? Don't you want the derivative of this? Isn't this the derivative? Okay, then solve for the derivative. Get y prime by itself. So y prime is going to be equal to y times x squared plus 2x plus 2 over x minus 2 times x squared plus 1. All right, if you're thinking, well, wait a minute, normally we have the derivative as a function of x. This looks like it's a cheat. Well, let me give you a second, right? Let me give you a second to think about what you could do here. How could you get your derivative in terms of x? Well, to get the derivative in terms of x, I need to get the y out of here in terms of x. Well, do I know what y is? I do. Y is equal to this. So all we have to do is substitute right here. And there it is. There's your derivative. You used logs to make your derivative easier. All right. Now, does this simplify anymore? Maybe. Am I going to simplify it anymore? No. If you had another professor, would they make you simplify it more? Maybe. But we have done our job. This is the derivative. Just so you know, there are many benefits to simplifying your answer, especially because normally we don't take derivatives just to take them. We normally want to do something with them, like set them equal 0 or something like that. But I just want you to understand that this is the derivative, just like 2/4 is 1/2. Whatever information you want, you can graph this, you can plug in an x value, whatever information you want, you can get it from here. Just normally we want a cleaner product, and we normally simplify it more. Okay. Now, that is going to conclude 5.1. When it comes to taking derivatives of the ln's of, like, let's say ln of cosine, I'm not going to go through it. We'll run into it in just a little bit, but it's still u prime over u. Okay, so it's more of the same. That's why I'm going to go ahead and conclude this lesson.